Good morning, afternoon, or evening, OT699. We've arrived now at week 7, and this is going to be the week where we combine several previous weeks together. So we're going to take that knowledge of hardware and Arduinos and loop it back to Python and computer programming. The objectives for this week, well, I'll start off with a tour of how Arduinos can communicate with a computer, specifically how we can get Python to talk to the Arduino, to read and write from it, and also to display data. We have also something a little bit different. We've got 3 guest speakers this week who are going to talk a little bit about their perspectives and experiences with a recent project that they all worked on together related to telerehabilitation. Miranda Donnelly is going to be coming in from an occupational therapist and occupational science point of view to look at how development of a new hardware and software rehabilitation program collides with user experience. How do you actually make sure that the intended target is able to interact with the new device/software in a therapeutic way that's good for everyone involved. Octavio Marampardo is going to come in from more of an engineering perspective. He's a PhD student in BME, and he's going to be talking about the nuts and bolts of this fairly complicated system that has been developed, which takes muscle activity data into an Arduino. But then this is the beginning of a full telerehabilitation program. So the data is saved, the data is visualized in real time. It's used in a game for the in this case, a stroke survivor. And so that's going to be more of the technical side. And then Coralie Fenord is going to come in and talk a little bit more about the Unity programming, which is going to be the game element, because that's what the end user is really interacting with. And so she's going to talk a little bit about how Unity, a software package, communicates with the outside world, things like sensors. They'll also come in for the synchronous portion. So you have a couple items of homework. The first is going to be to go through the tutorial on how to make Python talk to the Arduino. This is basically going to be loading some programs that I've sent you, making sure that they work on your computer by changing things like which port the program names as your serial port, things like that. And then after that, I'd like you to come up with questions for the guest speakers. So knowing a little bit about hardware, knowing a little bit about software, and what's involved in combining the two for an application, I'd like you to come up with a couple of questions and points of discussion that you can ask of this team who's going to be coming in. For the first part, which is going to be the more technical Python-oriented stuff, don't worry, you're not going to be doing a whole lot of line-by-line copy typing or coding this week. You don't need to know what every line in these programs means. If you look through those programs and can recognize the various pieces, parts, what this or that block of code is doing, that's actually pretty good, because then you can modify those. Or if you're going to go into this kind of field in the future at all for a hobby, this will be a terrific starting point for you. Also, if you're working with an interdisciplinary team at some point, it's good to recognize that this isn't easily Googleable stuff. A lot of computer scientists and engineers don't learn the stuff that you're learning. They've had to do it either as a hobby or for a project or something like that. And so if you are working on an interdisciplinary team to develop something, giving the tech person or the programmer a little bit of a boost or a little bit of a head start through these programs that I'm sending to you might actually be very beneficial for the team overall. So let's start with system integration and a couple things about it. Now, I mentioned that it's not especially trivial because oftentimes you have hardware and software that's updated at various different times, intended for different platforms, different operating systems. And if there's ever going to be a bug where one version of one operating system in the software world doesn't talk to the hardware that was developed for a different operating system, it's going to be in this element of integration, trying to get different pieces, parts to all work together. However, it's worth it though, because much of what we consider innovation is actually the combination of existing technologies in a kind of new out-of-the-box way. And for example, the team that's going to be giving some short presentations, they're using microcontrollers for medical data acquisition. Just being able to do that opens up a wide world of new potential for innovation. It reduces costs of things like teletherapy or biofeedback way down. It allows you to have people go home with the medical device instead of having to come to the fancy lab with the $30,000 equipment. So putting a couple of these little pieces parts together can actually be a very impactful thing to do. And so we'll learn a little bit about that from the guest speakers. Now to get a little bit more into the technical details, the most common way to get hardware to talk to a computer and the way that is most approachable for the most people, especially just starting out, is going to be through USB, the Universal Serial Bus. This is serial communication. And so accordingly, I'm going to cover the most common methods for bringing microcontroller data, like an Arduino's data, into a form that the computer can save and visualize and do all the things that computers are good at. And I'll start with reading serial data directly from Python. So first, the thing that we're going to need to do is set up the Arduino again. From a previous week, you had this circuit to be built. So pause the video if you're on the video and build this circuit again. Also, make sure you have this PowerPoint presentation open during the recording. It will probably help. So this, if you remember, there are a couple of wires going out from pin 13, which is a digital output, to a buzzer, which is number 1, and a light, or LED, which is number 2, and then goes back to ground. So whenever pin 13 is raised to high, you get a buzz and a light. Over on the analog side, we've got a couple of wires connected to this distance sensor. And so that's what we were playing with previously last week. We're going to use a little bit of both today. So create this circuit and come back when you've done it. All right, the next step is going to be to go into the Arduino IDE, and you've got two options here. One is that you can either take the full data acquisition code that you built last week and, for the sake of convenience, just remove all of the digital output lines, anything related to sending a digital output. And I've highlighted them here with some arrows. So this entire block in the bottom right about digital outputs, you can comment that out. Defining output pins, alarm thresholds, all of that can be removed. That's option 1. Option 2 is that I've uploaded a sketch called Week7 DAQ for data acquisition, where I've already done this for you. At this point, I think you've gotten what you're going to get from the actual process of moving the pieces parts into that program. So I'd like you to just be able to use this program today. So I've uploaded this already. You just need to take that file, put it with your other sketches, double click on it so that it opens like any other sketch, and run it. Now, when you run the sketch, be sure that the serial output is acting the way it's supposed to. If you go up to Tools and Serial Monitor, you should see a column of data, and it should respond to the distance sensor when you wave your hand over it. Now we're going to switch programming languages altogether and go straight into Spider in Python. So do that, and once you've opened Spider, in the console, which is the lower right panel in Spider, type in conda install PySerial and hit enter. That's going to install some serial communication libraries to Python, and you only ever need to do this once. It might take a minute. It may also ask you to restart your kernel afterwards. We'll get into that later. You don't need to worry about that for right now, and I have some instructions for that in this PowerPoint as well. Once you've installed the PySerial library, you're going to change a few small items in the code called readplotserial.py. The first change is going to be that you need to specify which port your Arduino is plugged into. I'm going to skip ahead now. If you don't remember how to find which port your Arduino is plugged into, in the Arduino IDE, you can go up to Tools, Port, and it will tell you. In this case, my port is COM3. Also in the very bottom of a sketch, in the bottom right, there's a green bar where it will tell you that this is an Arduino Mega 2560 on COM3, and so COM3 would be my port. On a Mac, it would look a little bit different, but it's the same idea. You go to Tools, Port, and you can look at which port your Arduino is on. Instead of COM3, it might be something like /dev/something, but it's the exact same idea. You would put that in where I've put COM3. Also be sure that the baud rate in the sketch matches the baud rate in the Python code. In this case, I've used 230400. You can make that as low as 9600 if your computer starts producing a lot of errors or seems to go very slow during these things. Also, be aware that there are two lines of code here. This import matplotlib and matplotlib use macOS 10. This thing here is sometimes necessary to uncomment if you have a Mac. It turns out in testing, we found out that some Macs actually don't want you to uncomment those, so you may have to try commented and uncommented and see which one works for you if you have a Mac. It seems to be some kind of weird interaction with Spider and Anaconda, and it may not be totally predictable, but it seems the problem is always solved by either having these commented or not commented. Now, when you run the code, you'll get two things happening. One is that the console will start outputting your distances in real time, and you'll also get a horizontal bar in a plot that goes up and down when you move your hand. When you want the program to stop, you have to go to the console and press that little red square that says stop the current command. If you hover your mouse over it, click that, and that should stop everything. If it doesn't, you can try clicking Control W on your keyboard or Command W. That will also break a loop if a loop goes out of control. Let me show you how that works on my computer. So if I go and plug my Arduino in and I run my sketch, it's thinking about it. It's a little bit slow when Zoom is going. Okay, and I go to read plot serial.py. I get some output here, chugging along. And in my figure, if I put my hand over the distance sensor, you can see there's a blue line moving up and down from 10 centimeters to 20 and back down again. And then when I stop it, I go to that red square. Back to the PowerPoint. So it's a relatively simple way to communicate with the Arduino, but it does have fairly slow reading times. It's only updating that plot maybe 10 times per second or so, which may not be ideal for all applications. And it's also somewhat imprecise in its timing. The reads are occasionally incorrect. You'll see 10 centimeters, 12 centimeters, and then all of a sudden a 0 or 140 or something. And that's because reading from a serial port oftentimes produces errors when you do it in this way. But that is the basic standard tutorial that you see oftentimes online for how to use Python to talk directly to serial. Before I go on, I'd like to just make a quick comment about the code itself. This is 59 lines of code, and most of it is setup. So everything up here, as we discussed previously, is just setting a couple of values like the baud rate or which port you're from. This max sensor val is just the largest y-axis value on the plot because it's a sensor, and I know what kind of centimeters I'm expecting. I can say 50 is probably about as much as I want to read. If you're just reading voltage values, you might make that 5. After that, it's just a few commands to say, hey, serial port, I'm going to communicate with you, followed by make a blank plot and put a line on it. That line will be updated later. Then there's a while loop, which just is similar to the void loop in your Arduino IDE in that it continues to loop forever. And you don't have to worry about this try except stuff very much. Basically what it's saying is it's going to try to read from the serial port. Sometimes it won't work. Instead of throwing an error at you and crashing, it'll just go on to the next iteration until it gets a value that it can use. Once it does, it will display that by updating the figure. And these are very common lines of code to create a figure that will be updated using these kinds of lines of code. You can copy paste a lot of this into other applications if you want. The only other thing to point out is this really long line of code right here where it's trying to decode what's in the serial port. When you get raw data from a serial port, it will have some kind of a letter combination at the end of the number. It'll be like a /n or /r or something like that. And that means that it's telling the serial port there's a new line. We want to chop off those letters and get just the numbers. That's what that whole thing is. Otherwise, it's fairly simple in terms of the number of steps. And the exact syntax is just a matter of finding examples either online or in tutorials. It's not something you would ever just know. It's something you kind of look for. So let's go back to the PowerPoint and move on to the next item. Okay, there's something called Fermata or Fermata. It's a kind of go-between software that we're using right now here today as a representative of many such programs that act as go-betweens between some hardware like an Arduino or other device and general purpose programming software. Basically, they handle all of the communication. They do all that serial port decoding and everything for you so that you can communicate more like a human to Python, and Python will then use this Fermata protocol to talk to the Arduino in Arduino's language. So you don't have to do all this yourself. An advantage to Fermata is that if you're using this particular software go-between, you don't need to have a sketch running in the Arduino. You just have the Arduino plugged into serial and you upload a kind of like blank sketch to it. And then what that sketch does is basically say, listen to Python. And then Python has a couple of lines of code that you can write to do things like turn the ports on and off or read from the analog input. So it allows you to not even go into the Arduino IDE and just write all of your code from Python if you want. And that can be good if you want to do kind of fancy things that take a lot of processing or display things in a nice way. So I'll show you some example of that. We can do this for both digital input and digital output. So the first thing that we're going to have to do, again, is go to the console in Spider and install the Fermata software. In this case, it's called PyFermata. So in your console, write conda install -c conda forge PyFermata as it is shown right here and press enter. That might take a minute. As before, it may or may not say you should restart your kernel before you use this. If that's the case, go up to the consoles tab in the main menu of Spider, and one of the drop-down items is restart kernel. You can also hit Control W or Command W after clicking on the console. So one of the things that you're going to do first is open PyFermata output demo.py in Spider and change the port to the name of your port as we discussed before. That's one of the only changes that you really need to do. The next thing that you're going to do is go into the Arduino IDE and go to File, Examples, Fermata, and Standard Fermata. That's going to be a sketch that's sort of like that's the sketch that says, let Python take over, basically, or another programming language take over, and run that sketch or upload that sketch to your Arduino. Once you've done that, you can go back to PyFermata output demo.py in Spider and run that. It's going to be closed the same way as before by clicking on that red arrow. So I'll show you how that looks. So first I'm going to go over to my IDE, File, examples, fermata, standard fermata. That's this sketch here that it brings up. It's an example that comes with the Arduino. Run this. It's thinking. Still thinking. There we go. It outputs a little song on pin 13 to let you know that it's done it. And since I've got a buzzer in there, you may have heard that. So then the next step is to go into PyFormata output demo and change the port to your port. I've already installed PyFormata, so I skipped that step here, but you should do it once and only once. This code is going to do something very similar to the Blink code that we started with. It's going to basically make a loop that goes forever. That's this while loop down here. And it's going to take the digital pin 13 and make it a 1. That means write the value high to it, basically. It's turning it on. And then it's going to do time.sleep, which is similar to Arduino's delay function. It just turns the board off. And then it's going to turn pin 13 off and wait another second. So it's going to create a blinking light. So if I run this, you can kind of hear that. And if I go to my content from second camera, you can see it's doing this. Okay. Now I'm going to unplug this for a moment, and I'll show you again how to stop that. If I were to run this again, you can kind of hear the beeping, and I go up to that red square in the corner of the console and stop it, and now it's off. Similarly, you can go into, let me get the PowerPoint up again. Similarly, you can go into the analog input pins. The analog input pins are just as quick to read from, just 1 or 2 lines of code using this PyFormata protocol. So then the next thing that you're going to want to do is open another .py file that I sent you called pyformata input demo.py. Again, there are a few small tweaks to that program that you want to try. First, this one's another one that I'm plotting something, so you'll have to decide whether your computer wants these 2 top lines to be commented or not, the import matplotlib and matplotlib.use macOS thing. And then once you've done that, you'll have to change your port again to the name of your port. And because this is a plot, it has a y-axis, and for now, since we're using the distance sensor, we can use 50. If you were using something else, you might want to make that something else. And then you specify here which pin do you want to read from. We have our stuff plugged into analog input 0, so read pin is going to be 0. So it's just those 2 changes. Now, this next slide isn't changes you have to make before you run it. They're just things I wanted you to be aware of, so I labeled it step 2.5 and step 2 5/8. Basically, if you were not using the distance sensor, you wouldn't want to have the distance sensor line of the code run, because that's going to be our calibration from voltage to centimeters. So you would get rid of that line if you weren't using a distance sensor, and then where you update the plot's line, you wouldn't use distance sensor as your variable. You would go back to something like board volts, or you would call this like potentiometer equals something something, and you get the angle of the rotation. Either way, this, instead of distance sensor, you would change it to whatever your sensor is that you're using, either the calibrated form, or you can go back to direct volts to be plotted from the board, and that would be if you used board volts in that line of code instead of distance sensor. So if you run that particular bit of code, it's going to be the same thing as before, where you can stop it by pressing that red square. I'll show you what that looks like. Now, we've already uploaded the Fermata sketch to the Arduino, so I don't need to change any of that. I just need to go to PyFermata input demo, make sure that my COM port is correct, the max value is correct, and that I'm reading from analog 0, and I can run this code. And it gives me the song again. Setting up the board, and you get a little line that moves up and down, 10 centimeters, 20 centimeters, back down. So this is working perfectly. So I'll stop that. Now, I should warn you that in some of these cases, when you're collecting data, depending on the speed of your computer, especially for older computers, you may see a line that's moving up and down as it should, but in the console there may be a lot of what look like error messages being spit out about missed reads or something like that. This usually happens when you're trying to make the computer do a little bit too much too fast. So the solutions for that would be things like slowing down the baud rate, or trying to put some sort of a delay where every time the while loop iterates, you wait for 10 to 20 milliseconds. So that would be kind of how you would tweak this if that's the case. So far, it looks like in a couple test cases, it looks okay for the most part. But let me know if your plot lines are very jumpy. Moving back to the PowerPoint. A couple observations. First, serial reading, no matter what you do, whether it's Fermata or direct, is going to be a little bit choppy. There's going to be some missed values that didn't quite read right, and you're going to have to deal with them. One potential way to deal with this is if you write a bit of code that collects several data points and then plots the average of those, rather than plotting every new serial read as an update to your figure. You can fill an array of, say, 10 values and do the average, very similar to how we did smoothing on the Arduino IDE side previously. Also, you have to be aware, as usual, that updating these plots by direct serial communication loops like this is very slow. So anything that you need to update more than like 10 to 20 times per second, you'd probably be better off going in a slightly different direction, and we'll discuss that in a little bit. But for basic things, and for force or a grip force or overall amount of muscle activity, things like that, this will be fine for all visualization purposes. You can't respond to a moving target that changes 20 times per second anyways. So if you're using this as biofeedback, this update rate is just fine. Also, this is all for columns of data. Modifications can be made to all of this code if you want to be looking at several sensors at once, but it gets a little bit more complicated. So for now, it's best to just focus on a single sensor. Now we're going to shift gears a little bit and go into what happens if you actually want the real data that your Arduino is spitting out. You want every millisecond. Every sample has a distance, and you might go back and look at that later and do some analysis. Maybe this is for research. If you want to save the data that you're getting from your sensor, you can't really do it with those serial commands because they kind of get a new value whenever they feel like it. What you want to do is really sample that data and put it into a file. And so now what we're going to do is a little bit of a trick. Instead of using Python for this, we're going to use a dedicated freeware. In this case, it's called CoolTerm. I've put this up on Blackboard. For Windows, it's a folder called CoolTerm Win. For Mac, it's a folder called CoolTerm Mac Universal 147. These will be zip folders. Once you unzip them, you can go into the folder and double-click on the CoolTerm.exe or .application or .dmg, and it doesn't need to install anything. It will just run when you do that. And this is going to be able to read your serial port, very similar to the serial monitor, but with the feature that it can write to a file. I'll show you how that works in a minute, but just a quick note of caution for those who are on Macs. Sometimes when you download these things and try to double click what was in the zip folder, you can wind up with a security issue. It's not really an issue, it's just Mac whining at you about not knowing who the developer is. So if it gives you something that looks like this, go to the system preferences, security and privacy, and you'll be able to see something that looks like CoolTerm's name or whatever else you've clicked on, and you can open it anyways. It's not going to hurt your computer. So then step 2 is to go back to your Arduino IDE and get out of Fermata and start writing to serial again using the serial writing program that we just started with today. Then you're going to go into the CoolTerm application itself and go up to connection, options, and you have 2 things you need to set. One is the port. If it says that it can't see your serial port, make sure that you have plugged in your Arduino and maybe you have to rescan the serial ports. Either way, you should be able to, in the drop-down menu, find which port you're currently using and set the baud rate to match whatever is in your sketch. So for me, I'm going as fast as I can on this computer. If it turns out that doesn't work quite well for you, you may need to drop that. But either way, those are the 2 options that you want to deal with. Don't mess with the other ones. And then press OK. And you should see something that looks very much like the serial monitor did in the Arduino IDE after you hit the connect button. It'll be scrolling down. One of the things that you can do next that's really cool is go up to connection, capture text/binary file, and press start. It will bring up a pop-up window that says what file do you want to save, and then all of the data that's coming out of the Arduino is being saved into a text file. It's not going to miss things. It's not going to update once every 200 milliseconds. It's going to give you exactly what you see in the serial monitor as a text file, which is really cool because then you have a fixed sampling rate. You can go back in later and do all kinds of analyses on it, and it looks exactly as it should. Before I get into how to extend this into some neat stuff, I just want to show you a little bit how that works. So if I go into my CoolTerm window, I'll just double click on that application. And since I am currently still running the Fermata code, I need to go back into Arduino's IDE and upload this sketch instead. This is week 7 back. Now I can go into connection, options, COM3 is set, but I need to fix the baud rate. Hit OK, connect. Now I've got my distance sensor values moving up and down as I change where my hand is located over the distance sensor. And I can go to connection, capture, start. I have a temp file that I've set up for this and save. I'm going to replace it. And now it is currently saving all of this data to a file. Now that can be kind of cool for various reasons. If I disconnect this and clear the data, I'll close this whole thing. No, don't save anything. This can be really cool because it allows you to write Python programs that actually read the last couple of values from that text file as it's being written. And then you don't have to deal with things like missed serial reads and things like that. It can also allow you to do things like read the last 100 lines of that text file and average all of them together if you want smoother data. This allows you to not have to do any kind of smoothing or processing on the Arduino at all. You can just have it sending out just the bare minimum to a text file, and then as you read that text file into Python, you can do all the fancy calibration and math later before you just update a plot or display it, and that can oftentimes be much smoother and faster. We're not going to get into all the details of it because as you start doing that sort of thing, you get into all kinds of file paths and potential bugs that can happen with Mac. Most of them are completely solvable. If you're interested in doing this kind of thing, contact me and we can go through how to do it on your computer. It's just not something that was very good to show general purpose. As a quick demonstration of what kinds of things are possible, though, I wrote this little demo code, and you're not going to work with this one. It's not that good, but it shows you what the next steps would look like. So if I run this, I've created a PyQt5 GUI, a graphical user interface, with a window that would be for my subject and a window that would be for me for controls. And I can click Setup Acquisition. This will open up the CoolTerm window. I can then go to Connect, Options, set the baud rate correctly, say OK, connect, then capture that data to a text file, which I'll call temp.txt, replace the old one that's there because I don't care about it, and then hopefully with any luck and Zoom being pleasant to me, I can start making some plots. Okay, so there you go. I've got a little text in the upper right-hand corner. I've got a moving slider, and I've got a window for the participant to use in case this is some sort of a biofeedback. So all of this is possible. I can stop the plot, get rid of the terminal, but again, this is a level that requires a lot of tweaking for your specific computer. I just wanted to show you what is perfectly possible with just a few lines of code and the types of software you already are familiar with. So let's go back to the PowerPoint for 1 second. As far as extending this, I've covered most of it. The data that you get from reading a text file is actually a little bit better than the data you get reading serial directly. And one of the reasons why you would want to have visualization in Python in the first place is exactly because you can make an app that controls all the various aspects of data acquisition and plots according to what sensors you want to see, and all kinds of options are available to you. In fact, matplotlib, the library with all the plotting functions, it has a function called funcAnimation, which allows you to animate these plots and update them in real time in a better, more straightforward way than having to write your whole program in a never-ending while loop, which is what we've been doing mainly today. So there's some options out there so that you just can be aware of them. This is the fundamentals of data acquisition, though. You can either read from the serial port directly while the Arduino sketch is running and spitting out serial data. You can use an intermediary software like Fermata. Some devices come with their own software that allows Python to communicate with them, so you can use those. And then the third option is to go to some neutral platform, like have your Arduino spitting out data to a text file, and then have any programming language that can read a text file repeatedly take data out of it and use it for display. Now, the templates that you have, of course, there's a lot of code in there. I don't expect everybody to know every single line and be totally comfortable with that. But if you wanted to learn about this in the future, one of the best things that you can do is take templates that work and start to modify little bits and pieces of it and become familiar with certain blocks of code that are always repeated when you do this sort of thing, and look those up. And that can be a tremendous acceleration for future learning. It also helps to be able to identify exactly what you need in an interdisciplinary team. So if you had an idea for a sensor that you would want to be read into a computer and displayed in a certain way, instead of saying, I need somebody who knows programming, you can say, I want a plot to look like X or Y using Python rather than this example here that works, and somebody who knows a bit of programming can jump off running from that. And the same thing for if you wanted to be able to control digital inputs and outputs, motors and devices and stuff with Python, you could say, I want to use PyFormata to control digital outputs on Arduino using a Python script. I have some basic examples here. Now I need something a little bit more fancy than I can do. And you can find somebody who is able to do Python coding and understands what PyFormata is and has used it as a hobby in the past. And you can go directly to somebody who knows exactly what you want easier that way. And that's really fundamental to system integration on the fly, because not everybody has the time to learn all of this. It's not really standard curriculum everywhere to make Python talk to an Arduino and to have that talk to something like Unity. And it's something that a lot of people have pieced together through months or years of effort. And with that, I will end my portion. All right, so without further ado, we can get right into the guest speakers now, starting with Miranda Donnelly.
Hi, I'm Miranda Donnelly. I'm an occupational therapist with experience in outpatient and inpatient rehab with adults with neurologic conditions, and I am a PhD student in Dr. Lou's lab. And today I'm going to talk a little bit about some of the roles that OT can have in the development process. In short, the role that we can have involves us using the same skills, the same theories and strategies that we bring to clinical practice, just applied a little bit differently. This figure is from the OTPF3 because I like the figures in that better than the 4th edition. And this just shows an overview of our domain and process. So we see this whole picture of context and environment, patterns of participation, and client-specific factors, their skills, abilities, motivation. And we see how occupation is imbued with meaning. And so I also want to point out that this figure shows our iterative process of evaluation, goal setting, and intervention. That isn't fully linear, right? We are constantly reevaluating, even within a session. What are we doing? Are our goals still appropriate? Do we need to shift any of this so that we can best meet the needs of the client? And we're going to talk about that iterative process a little bit more. So our perspectives of occupation are rich and can bring a lot of value to the development team, even if our expertise is not in the specific technologies. There's a lot of ways we can apply our OT expertise to tech development, but we can just touch on a few examples here. So first of all, we have a good understanding of ability, disability, and kind of where abilities and participation intersect. We can be attuned to these other factors so that we can create inclusive designs, systems, spaces, experiences. We're very attentive to details that can transform a tech product, for example, from something that's only really usable by an able-bodied clinician or caregiver into a product that's actually more accessible to a broader population and has fewer demands for use. We can also help be consultants on projects that want to improve accessibility, user experience, stakeholder engagement, particularly is something that's kind of on the rise and something that we are used to doing. We're used to engaging our families and our patients really at the first stage of the process. We can be good at universal design, kind of identifying what the real problem is and the related context that informs that problem. So we can study the effectiveness of our device or product at any stage. Two concepts in OT that are very common that we use all the time in our practice are adapting and grading activities. So we learn to do this not just from a big picture perspective, but we can do that on the fly during the session, right? We're adapting in vivo, troubleshooting what's working, what isn't working, and how we can improve the session or the treatment plan. And that kind of creative thinking and problem solving is really important for that iterative process of figuring out how a product or a device can best serve the client. We're also experienced working with a multidisciplinary team, right? We're used to working with people from all different health professions, and that same kind of communication skills and translating knowledge from different areas of expertise is still going to be applicable when we're working with people like engineers and software developers and product managers and other people on the product team. I'm going to show you something in a moment that just kind of demonstrates that the end user is oftentimes actually excluded from the development process for new products or devices, or at least their inclusion isn't until way too late in the process, in my opinion. And I think this is shifting, but a common approach is to have an idea, make a prototype, and then see if the target population likes it. And then sometimes after millions of dollars or hundreds of thousands of dollars and a lot of time have been invested in this product, they receive major feedback, maybe saying that this product really is not meeting the need or it's not what the user really wants. And so if we're involved early on in the process, and if we get the end user involved, maybe a certain client population involved early, we can hopefully identify, is this device that they've created or invented or thought of really going to meet that need? And if so, that's great. How can we support that process? And if it doesn't, how can we identify what the real problem is and help create something that's going to better meet that need? For example, we don't just in OT give our clients goals, right? If we were to come into an eval session and say, here are your goals, we're not doing occupational therapy. We've really missed the point. And so we can bring that same concept to the development process. We can include stakeholders from the beginning, whether that's a patient population, a care partner, other clinicians, hospital administrators, anyone who will later on be interacting with this product. And so we can involve them from the ideation stage before we even set goals for the product. I do want to note, though, I'm not trying to speak ill of product teams or the development process. I think everyone's, for the most part, very well intentioned, but any of us working on partial information aren't going to be as successful as we are when we're going to work together and share knowledge and expertise. We can then maximize the benefit of that innovation, and it's a team effort. So that's why we're going to talk today about what we can bring to that team. And just for some context, there's lots of OTs employed as clinical specialists, product managers, process and product consultants, trial researchers, UX researchers, clinical managers. There's people in product sales and clinical relations. OTs have founded tech companies. They can be involved in the training process that clinicians know how to use the product, customer support, etc. So we have lots of potential roles in tech companies, and there are OTs working in those roles now. I just put a few quotes here for your reference on what the OTPF, the fourth edition, says about technology. And I think a lot of times we're talking about maybe this third bullet, maybe in this course specifically, about these virtual interventions. And telehealth, as we know, is very prevalent right now during COVID, but I think it will continue to be afterwards. And so we need to be able to adapt those environments and help make the most of those experiences for our clients. This is that image I told you I was going to show you. This is from a 2019 systematic review of clinician involvement in early health tech assessment during the innovation of medical devices. And the red box here on the bottom left quadrant, this is where the early assessment of devices is happening. This green box over here is where clinicians are getting involved. So oftentimes clinical perspectives aren't present during the basic research or deciding kind of what's the best product to fit the problem. They're not part of the process often to demonstrate that this product is even going to be effective and creating the initial prototype. So if you think back to some of those examples I just shared of how OTs can help the development process, you might see that we can make a lot of very valuable contributions early on. So imagine if we only join in during that green box. Millions of dollars have maybe already been spent, lots of time and energy, and it's quite possible that when we do our clinical evaluation of it and clinical trials, we might find that the device doesn't fit into people's lives, that they've spent their own hard-earned money on something that's not intuitive, that doesn't meet their personal needs, or that's too demanding for them to actually use. Maybe it's not motivating or doesn't actually achieve the goal they had hoped. And so we want to prevent that because no one wins in that situation. And by taking this class, you're already taking a really good step towards being involved in those early stages because you're learning the vocabulary of technology that OTs don't typically have. And it can sometimes feel like a foreign language, at least to me, and I know to others as well. So I think it's really important that you're learning this language and can engage with people with more technical backgrounds to really problem solve together and bring both of your expertise together to really benefit the end user. So I'm very fortunate to be a collaborator on the current phase of reInvent, which is a product that Dr. Liu and her other lab members have been iteratively designing for many years now. And in short, it's a human-computer interface that personalizes and gamifies chronic stroke rehab for people with upper extremity paresis. And it uses their real muscle activity to influence gameplay, and that provides this very engaging biofeedback experience that can enhance recovery. And our lab is multidisciplinary by design. It's a very supportive environment. Everyone's perspectives are valued, which is wonderful. And given that Dr. Liu's an OT and our lab has the goal of personalizing rehab interventions, my role hasn't been some of what I just described, which is, when some people have to come in and really advocate to be involved early. That's been happening since day one of this project. Everybody's been involved as far as, different clinical and engineering perspectives. So throughout this process, I have a few different roles, and I'll just share for this specific project kind of what some of those roles have been. So I help kind of consult on which games are being developed and how the user is going to participate and engage with the game. I'm looking at how the hardware is applied to the person. In this case, we have sensors on their arm, and how this whole computer and reInvent system is set up in their environment. I'm looking at other contextual, temporal and performance skill demands of the hardware. I also want to look at the software. What is it like to navigate that and set it up? Is it accessible? Are the menus and participant interfaces intuitive for both the client and the clinician? I also want to know, what can we customize about this so we can make it really personalized for therapy? And when we're studying this, which outcome measures are going to best capture those desired outcomes that we have? I'm also curious about the clinician-client relationship. Is our platform facilitating that therapeutic relationship, or is it getting in the way? I also want to make sure that any other materials we provide to the user are supportive and supplementary as opposed to confusing. This right here is just one way of visualizing what it means to iteratively design and test in tech. Of course, there's lots of different visualizations, but I like this one. It kind of shows that, after this, learning and discovery phase, you design, it can almost look like you're moving backwards, right? You're redoing maybe work you've already done and you test it, but then look, it gives you the momentum to move ahead with a product that's better. So these iterative design processes it just continues. And it's so valuable in how we end up developing products that are very useful. So I want you to remember what this looks like. And now I'm going to switch over to this view, which is again from our OTPF, the third edition. And so I want you to see the similarities between our process and the design process. It's a cycle of collaboration, and it includes analysis and intervening, measuring, and integrating what we've learned into next steps and improvements. And so I'm going to be asking a lot of questions at each stage of our process. And sometimes those questions are going to be the same at each step, but it's going to all depend on kind of the decisions we're making as a team. So as I'm sharing examples, I'd like you to think about this figure on the slide and also think about the client population you'd like to work with, because my experience is, of course, going to be working with mostly older adults who have neurologic conditions. So we're talking about which game should be developed. I'm asking questions like, what skills or movements can this game address? I'm likely to prioritize games that are going to address multiple skills or movements, so we can make the most out of that specific gaming experience. And is the game going to be engaging? So will the client want to keep playing, or are they going to get bored after a few rounds? And what are the motivating factors in the game? Like high score, are there multiple levels? Are there new and changing challenges throughout the gaming experience? And I am not knowledgeable about game theory, so I rely a lot on Coralie for this. And some of our conversation kind of revolves around how we can incorporate her knowledge of game design with my knowledge of rehab and what might be very possible or what might be very frustrating for someone with a disability. And when we're thinking about how the user participates with a game, I'm thinking about how our stakeholder is actively using it during the testing process. What time of day are they using the platform and for how long? Are they too fatigued after they use our platform to participate in their other occupations? Because I don't want that. Are they experiencing pain or discomfort outside of the therapeutic range while they're participating? Do they feel they're working hard enough, too hard? Do they feel they're benefiting from the platform? Someone's not going to stick with something if they don't think it's really helping them. And do environmental and contextual factors influence how or when they're participating or using this hardware and software? So if they work, maybe they can only participate it in the early morning or in the late evening. Do they have a very busy household with lots of people distracting them and it makes them hard to set aside that time to participate? Is there a dedicated space where they can set up and comfortably sit in an ergonomic chair and participate? Are there environmental hazards that make them worried to participate? Do they need a care partner to help them don or doff the sensors on their arm, or can they do that independently? Are they feeling frustrated by the challenges of getting the sensor placement in just the right spot on their arm, or is that something they're achieving really well? And how long does the setup take versus how long do they actually enjoy the platform for? Is that balance worth it to them? When we talk about the design and use of the software, our whole team is considering, are there too many steps between setup and actually starting the game? Are there too many buttons to click? And is it clear what the next step is? Is it intuitive to kind of go through that flow? I'm wondering, are the menus and overall interface visually cluttered, or are they easy to process? And are there features that help the user navigate through the system and see what step is next? I'm also curious, what errors are going to pop up, because it's tech, of course, but we have to plan for things not going perfectly. Is it something that the user can easily troubleshoot? And if not, are we accessible to help them out? And are we creating an experience where the participant feels comfortable reaching out for help versus just kind of giving up? When I look at the resources we're providing, do we have too many words, not enough words? Do we have visual cues or options for them to listen, auditory information, not just reading what's written on a screen? I also want to consider what can we customize about the platform. So from a clinician standpoint, does using a session in does using the platform in one of my clinical sessions still require my professional judgments? Personally, I'm hesitant to use any device in my practice that doesn't require me to use my training. Ethically, I'm not going to bill for something that the client could do completely independently. So if we want this product to be used in a clinical environment, there's different considerations versus a product that we want people using fully on their own at home. In the case of reInvent, we're trying to account for both situations. So we have some guided sessions, some independent sessions. So we have two interfaces, one for the client and one for the clinician. And the clinician can then customize things like dosage and timing, difficulty, which game options appear for the participant at any given stage of their recovery, how fast are stimuli coming onto the screen, and how kind of simple or complex is that participant view. We also want to make sure this doesn't put too much burden on the clinician, and what technical skills are going to be required to operate it. Because again, OTs don't typically have that kind of technical training that you're getting. And does this platform enable ease of communication? Does it enhance the therapeutic relationship or get in the way of it? Another big thing is, does the user or the client have choice? We know that agency is huge in occupation, and we're always encouraging patients to make choices and take ownership of how, when, where, and what they participate in their lives. And so this is no different. We want to make sure people have options. So in reInvent, we actually have an option for, since we have body representation, they can actually see their arm in the game. We have an option of what that arm looks like. So Corley programmed the game such that the user gets to choose which arm they will see based on how they identified. So you can see the 6 options we have up there. Does the user have a choice of which game they play and how many rounds? Even if as a clinician I recommend a general range, they can kind of customize that based on how they're feeling that day. We can also incorporate outcome measures that capture the effectiveness. We need to do that. And so what are the actual skills or occupations that we expect to be changed by the intervention, and are we measuring those? A question I love to ask during this process is, what questions or topics did you expect me to ask about that I didn't? And that gives me so much insight into what I'm missing. I think that also is a great trick clinically too. And then I ask them to expand on that and tell me a little bit more. So that tells me, did I ask the right questions? What questions am I missing? And then I also ask myself and the client, did I ask too many questions? Was that assessment process just too long? I'm also wondering, are the assessments I'm giving feasible in a clinical environment? And the same thing's, again, going to go for that the proportion of setup time versus playtime. Is that feasible in a 1-hour session, for example? I, of course, want to use evidence-based interventions. I think there's also a really good balance to include some custom surveys that really home in on your specific device or platform to make sure you're getting device-specific feedback. And at what time points can I use these measurements? For example, if I'm going to use something like the stroke impact scale, I can't be using that every single week because it's just not sensitive enough. It's a scale with every question has a 5-point Likert question. So it's not going to be sensitive enough to determine change within a week. So I need to make sure that the assessments I'm choosing line up with my evaluation timeline. And so how do we present this product to the prospective user? Is our language inviting and inclusive of people from different backgrounds, experiences, and literacy levels? Do people who are not tech people interested in engaging in our technology, or does it kind of scare them off? Do we convey our genuine interest in their feedback and ongoing participation, because that's going to influence the type of information we get back? And do we provide the materials to help them be successful? When I think about the logistics of the product, I want to know how much does it cost to develop, and does that cost actually match the benefit and value that they're getting from it? There's some products that cost tens of thousands of dollars to the client and only really help them achieve one motion, for example, grasp and release. And for some people that might be worth it, but we have to evaluate, is that one movement worth so much money, time, bulkiness, for example, if in the case of like an upper extremity exoskeleton, is it worth that expense for the simple movement that you're able to achieve? Does that product fit in the routines and habits of the user, or is this going to be just a glorified paperweight? Is it durable? If a user drops it because of a tremor or a motor skill deficit, is it going to break, or can it withstand that use? And are we including enough kits and enough tools in our kit to be helpful, or are we including so many that it gets confusing what they're supposed to be using and how? And how many pieces is the user responsible for putting together? We want to minimize that, so it's all kind of compact and put together. And finally, I just want to emphasize that role of the iterative process. So no matter what expertise each of us brings to the team, we're not going to create an optimal product on the first try. And we need to be okay with that and okay with learning and admitting that we're wrong. Maybe I test a hypothesis and I was just flat out wrong. That's okay. That's part of the process. We just know to move forward with that information to make the best decision we can in that stage. We're constantly testing. We constantly need to have our participants involved, that target client population, so that we don't overlook something that someone who maybe is able-bodied might miss. We want to always be asking for feedback, and we also want to value the subjective truths just as much as the objective truths we're gathering. For example, there have been a few times where our system had a little glitch that made the calibration inaccurate. And without knowing that objective truth, the user during that session said they felt really in sync with the platform, which probably shouldn't happen if the calibration is really off. But both are true. That subjective experience of feeling in sync with the platform and the objective truth that the calibration was wrong are both true and important for the development process. Just want to briefly touch on clinical reasoning. I won't go into great detail here, but I do want to show you that the same kind of professional and therapeutic reasoning we use in our clinical practice is relevant here. This slide comes from something I was reading about in Willard and Spackman, which is that big purple occupational therapy book that you likely have as part of your course reading for another course. And there's these cognitive processes that help us develop our professional reasoning, but actually they help us develop products and devices as well. It informs our thinking. You know, we're trying to pick up on cues. We're trying to see what is the most important information at this stage that I should be picking up, kind of like playing detective. And with that, are we seeing patterns of use? How are people engaging with this device? What are the similarities and differences? We also need to understand, of all the problems that we see maybe with the device or all the issues we're facing at a certain stage, what's the most important part? What's the most important problem we can address right now? And really home in on that problem. Once we know what the problem really is, we can then develop a better outcome. And we can really focus in on what we can change now that's going to make a big difference. And finally, we have all of our different types of clinical reasoning, and I won't go into great detail about these, but we're using these at every stage. You know, I've talked a little bit about the ethics of comparing the value of the device with the cost, the time, the energy, the money involved. I've talked about kind of how does this condition affect someone's life, and how does this device meet a need within that narrative of that person's life. Procedural, I want to know, you know, what assessments make sense, and how are these types of devices typically used in the clinical space, and will our device fit in with that as well, if that's our goal? And of course, scientific reasoning too. You know, we're testing hypotheses constantly and making decisions with the best evidence that we have available to us. So there's examples for all of these, but for the sake of time, I'll let you kind of think about how you could apply this clinical reasoning based on some of the examples I have given you in this presentation. Finally, I just put together a few little ideas if you want to keep developing these skills. These are some things I have found helpful for me to do as well. And a lot of it is really just reflecting on our own use of technologies and using our professional reasoning and OT knowledge to really just evaluate what that experience is like. And if you were on that development team, what would you suggest next? And what kind of questions would you be asking? Last thing, I just have a few resources here. Just if you're interested in exploring more about what OTs can do in these maybe non-traditional roles, working for tech companies or just in the tech development process as a consultant. So I will make sure you have this slide so you can follow the links to a few different resources. Feel free to reach out to me. I'll also be in class on March 4th, so please do bring your questions, and I look forward to our discussion. Thanks.
All right, so our next speaker is Octavio Marin Pardo.
Hello, everyone. My name is Octavio Marin Pardo, and I'm a biomedical engineering PhD student working in Dr. Liu's laboratory. I did my undergrad studies in mechatronics engineering, which essentially consists in merging electronics, computer engineering, and mechanical engineering to create integrated systems for different applications. Here, my research is centered in biofeedback of muscle activity to promote recovery of the upper limb after people had a stroke. So to work on that, one of the projects in our lab was the development and testing of a system that could measure and process in real time these kinds of signals. So we call this system reInvent, and basically it's a modular system for acquisition and processing of muscle activity, or EMG, to provide personalized feedback as real-time control of computer games. As I mentioned before, we developed these to improve motor function after stroke. So To do this, we measured the activity from the wrist extensors and flexor muscles and created games to provide positive reinforcement when the system detects an attempt of wrist extension. Of course, development of these kind of systems requires not only to know how to connect devices to the computer, but also what to know with the information that we acquire. Design and development of technology is an iterative process where we continuously test solutions to meet the needs of our users and their expectations. So my role in this project was first to identify the needs of everyone that will use the system, being researchers, participants, or clinicians. Then I had to translate those needs to specifications and develop the hardware and software that complied with those specifications. To do this, we need to answer questions like, how are we going to present information to the users, and how are we going to read information from them as well? How are we going to acquire and store the data? Meaning, what type of sensors are we going to use? How many? How fast are we acquiring things? Also, we need to know how are we going to process this data. In our case, it means how are we going to translate the signal that we are measuring and translate it into the behavior that we want to train. Finally, we need to know how to connect everything together. What information each component needs. How are we going to transfer this information when an application is going to do something? So first, we need to define everyone's needs. First, we need to acquire data with good quality because we want to provide accurate control and also to analyze the signals that we see afterwards. Since we are interested in electrical activity from the muscle, we need to record fast. Whatever we do with these signals must be translated to something that is a proxy of the behavior we want to encourage. Related to that, we also need to provide real-time control of the games that we create. Finally, since technology keeps getting better and faster, we need a system that is easy to update, but only for the pieces that require so. Most importantly, since people with different backgrounds and computer literacy will use it, we need something that is as easy to use as possible. So now that we have all of these needs, we translate them into specifications, which is another word for saying something that is quantifiable and that will define the inputs and outputs and constraints of our system. So all of these essentially will be translated as, we need 4 EMG sensors. We need to acquire at 2000 Hertz. We are going to calculate a ratio of activity from the 2 wrist muscles. With this ratio, we're going to have 3 types of control for the games. Could it be binary, meaning it's the right or the wrong kind of movement that we're looking for? It could be discrete, meaning you're doing an extension, or you're doing flexion, or you're just co-contracting. Or it could be a continuous measurement. It's something that looks more like an extension or looks more like a flexion. And finally, for the flexibility and easy to update things, we developed the system to be modular, meaning that every component would function independently from each other, but together. So briefly, reInvent is comprised of 5 independent and distinct modules. We have acquisition, processing, games, interfaces, and data storage. All of them have their own specific requirements in terms of inputs and outputs. So previously, you learned how to write a program that uses an Arduino and read a sensor and show that value in the computer screen and save it. Here, we did exactly the same thing. However, since we needed to record from multiple sources at the same time, we used another application to connect, synchronize, and record all of the outputs. So I will talk a little bit about each component very briefly. So to ask the participant or the clinician about the information on how are we going to configure the system for their use, we wrote a program in C# to create graphical interfaces where people could select different options for each game. This same application also deals with things like managing directories, write configuration files, open and closing other modules of the system, and so on. A couple of the key challenges here where we need to know what to ask. We need to open and close applications. And we need to know how are we going to communicate information between one module and the other. Similar to what Dr. Lane showed you about Fermata, we created an application in C# that communicated with an Arduino to retrieve the values that each sensor was reading. Here, our main challenge was to reach a fast enough sampling rate that could allow proper processing of the data, both, as I mentioned before, for good control and to analyze the data afterwards. About signal processing, to translate the electrical activity from the muscles, we created a program in MATLAB that would compare the value from each muscle and calculate a ratio of activity. It is important here to note that this required to calibrate the system. That is, the system needed to know when each muscle was active. To do this, what we did is compare the values that we were seeing from the muscle at that given time and compare it with what we knew was the activity when the person was grasping an object. A main challenge here was to define how the behavior that we want to encourage is going to be translated as something that the game would interpret to control the environment. This had to be simultaneously done for both the processing and the game modules. So once the system was able to infer what the participant was doing, that information was used in different game environments to control animations and provide rewards when the signals match what we were trying to train. Since we also have an expert in this area, she will talk a little bit more about this. So in summary, first, for a successful integration of hardware and software, we need to identify the needs from the users and the components of each subsystem. With those needs, we need to translate it to specific and quantifiable requirements. As you saw, for a couple of things, we created programs to solve our specific needs. However, some requirements could be met with existing technology, like what we use to send data back and forth between each model and store it. So it is important to be efficient and effective, and that requires a balance between using something that already exists and having someone with the tools to develop what it doesn't. So, as I mentioned before, this is an iterative process where we need to continuously test, not only to ensure that the technology works, but also to know that we are meeting the expectations of our users. This is why it is essential to keep the users as much as involved as possible. Feedback from them is essential to create meaningful and useful technology in healthcare. So that's it from my side. Thank you very much, and I will see you in class for any questions that you may have.
And finally, Coralie Fenord.
Hello. So I want to talk to you guys about the ways that we can incorporate information from the environment into our VR experiences. So at the most basic level, we can track our hands. So this is an Oculus Rift, and it comes with 2 controllers, and these guys are able to track both position and rotation of our hands in space. As an added bonus, because they track button presses, they're able to approximate our finger positions based on the buttons being pressed. And this makes the experience feel a little bit more realistic. So if we take this to another level, we understand that the controllers are essentially trackers. If we were to place the controller on a moving object, we would be able to represent that moving object within the VR experience. So HTC Vive allows us to purchase tracking pucks in addition to the headset and the controllers. So when we think about it, we can track any number of things specifically moving things. And so this creates a world of opportunities. So here's an example. If we were to place the pucks on specific body parts, we can then have full body tracking within the VR experience. So I worked on The Lion King a while back, and it gave me the opportunity to see some of the wonderful ways that we can use tracking pucks. So for background, The Lion King aimed to solve an age-old issue in the animation and visual effects industry, and that's how do you film, how do you direct a film when you can't see everything in the environment? You're not able to be in that world and choose the right camera angles in the way that you would in a live action film. So with the introduction of VR into the technology industry, we proposed a solution. What if we film the entire movie in VR, and what if we film this movie as though we were filming a live action film in a live action set? So this is where the pucks became useful, because then the filmmakers were able to use all of the same tools, technology that they are used to using in a typical live action set, and we're able to track these tools with the pucks, and in that way they have a similar experience to their typical one. So this video shows us a little bit more on this.
When we thought, how are we going to approach life? We knew we needed to do something new completely, and we had the idea to do this in virtual reality. Take the tools of virtual reality and apply those to filmmaking in a way that's never been done before. We built a video game, the purpose of which is to make a movie. Inside that video game, instead of cars and guns and points being scored, we've got cameras and lights and lions. So we go inside the volume, which is this technology blank space, this space that's filled with grids that hold virtual reality sensors, things that tell the computers where virtual cameras are in space, or virtual Steadicams, or virtual dollies, or virtual cranes. These all look like and feel like real filmmaking equipment, except there's no camera attached. There's just a sensor that says, hi, I'm a camera, I'm over here, I've got a 50mm lens on, I'm looking downward at 20 degrees, and there's a line. And it's just as if you're playing a video game, except instead of controllers, and we do use controllers at times, we're using tripods, we're using wheels, we're using Steadicams. So we're giving the filmmakers all the analog tools that they're accustomed to. Their instincts are reliable, but the output is all through this real-time gaming. Yeah, let's just back up the animation. You need to be a hair lower, though.
All right, so now more recently, we have the VR companies are incorporating more precise hand tracking. So the Oculus Quest, which is a mobile VR headset, has recently incorporated hand tracking sensors within the headset. And that ends up looking like this. And we can see how this can be super useful for people who are not able to hold a controller. Now the Valve Index also incorporated hand tracking within their controllers. So it looks like this. And you can see here that we have the best of both worlds happening. We're able to both have precise finger positions as well as button presses. So everything that I just showed you, these are all things that are included in the VR headset technology. So for example, the Valve Index that we just saw, the controllers come with the headset. And so if we want to make a game that has precise finger tracking, then we can then use their controller. But what if we want to track something that we can't track with the device, the headset itself, and everything that comes with the headset? So lucky for us, a number of companies are developing add-ons for VR headsets. So essentially they have a sensor that tracks whatever it is they're trying to track, and they connect it to the VR headset and to Unity. And we're able to access it and write code because they provide us with an API or an SDK. And so an API is an interface that allows software to interact with other software. And an SDK is a software development kit. So either way, we're adding a set of tools or a package into our Unity project. And this way it allows us to use information from the device or the sensor into our VR experience. So a specific example is this company called Week7 Labs. They developed VR-compatible brain sensing technology. Now I want to give a disclaimer. Dr. Liu is very skeptical of these sensors' ability to actually track EEG data accurately, which makes sense because this is not the best positioning for doing this. However, I wanted to show this as an example because it demonstrates that the industry is looking into ways to incorporate EEG into our VR experiences. And also it'll show us an example of how we can take an API and use it within Unity to connect the sensor. So let's take a look at the website. So I want to bring your attention to this little blurb where they explain how these connect. And it's basically a rehash of what I said. So the Week7 link is added on to the HTC Vive Pro, essentially the headset of our choice. And it senses EEG signals, and by means of their software, it allows the user to take advantage of the commands in the API to apply EEG into the environment. So from here, we would essentially download their package, which we could do, I'm assuming, from here, and incorporate that into Unity. So let's take a look at another example. Another company is called Ultraleap. They develop a number of solutions to allow us to interact with technology hands-free. Well, not hands-free, but controller-free. So here we've used the leap motion, which we see on the left. So we have a sensor that is placed on top of the VR, in front of the VR headset, and we're able to fully track hand movement. This is similar to what I showed you with the Oculus Quest hand tracking. Now, this was created before the Oculus Quest incorporated the hand tracking into their headset, so it was super useful then to be able to connect the sensor to the VR headset. And honestly, since the Oculus tracking is not super great right now, this is still useful. So let's take a look at the website here as well. So here we would also try to find where we can download the package. So here I'm looking for where they have the developer package, and then it says develop, and then here we see Unity. So they have a package specifically for Unity. And here we would download this. Now let me quickly show you an example of a game that we built using the leap motion. So this is a game called Asteroid Attacks, and it's a game that encourages repeated use of the upper extremity for children participating in rehabilitation for stroke or other conditions. So let's take a look. All right, so I want to show you a little glimpse of what that looks like within Unity. So here we see these two folders, Leap Motion and Leap Motion modules. So this is what we get after downloading the API or packages that I showed you on the website. Now from here, within that, they have a number of things. So they have scripts that allow us to use the Leap Motion and connect it to the VR headset. They have prefabs, which is especially useful because I can just drag and drop this. And specifically here, I essentially have an object that represents the headset as well as the Leap, the sensor on top. And it also gives us access to the hands. So if we look at a script, whenever we want to incorporate a package or an API into a script, we want to tell Unity that we're using it. So you would say using leap.unity. So from here, we can access scripts from that package. And here is an example of a line where I do that. So within the scene, I look for an object that has the component Leap VR camera control, and I know that the object that has that is the player, is where the player's head is, which, as you can understand, would be also where the sensor is. So from there, I'm able to do a lot of programming with the player through that line of code. Now, going back to the slides, so what happens if there isn't an API or an SDK available for the object that you want to incorporate into VR? So say you want to use an Arduino or a light bulb in order to, you want to use those in your VR experience. So the good news is, since Unity is fairly popular and widely used within the gaming world, there's a lot of free material online. So, and there's likely a lot of open source code within GitHub. So essentially, you could write Lightbulb API Unity, and you might find a package that allows you to interact with a light bulb through Unity. So here's an example where I did this with Arduino. I Googled it, and this is one of the first things that came up, and they provide us with code in GitHub that help us do just that. All right, so another thing that we can also do is we can try sending and receiving data by reading and writing to a file from both applications. So say we're using Arduino. From the Arduino side, we can try to write the data, and then I can read the data in the text file from Unity. And this allows us to communicate in that way. So in reInvent, we use some of these techniques. So reInvent is a suite of games that we're building that helps stroke patients with rehab. And here I want to point out that there were three ways that I wanted to interact with the environment outside of Unity. And the first is I wanted to receive information from the clinician or researcher. The second is I wanted to be able to read data from the muscle activity, so from the EMG sensors. And then the third is I wanted to send the scores to the clinician or researcher. So for the first, in order to receive the settings, I do what I mentioned just before. I read a text file. So, and this is where the concept of black boxing comes in. I don't need to know everything that's going on, but I know that I need to read a specific text file, and I know that on the side of the clinician's interface, which Octavio is working on, that he will write information within a text file, and I can read it within Unity. And second, I want to be able to read data from EMG sensors. So lab streaming layer is an API that researchers use that allows it allows researchers to synchronize streaming data across devices. So I'm able to set it up in Unity, and from there it's able to read data from outside Unity. And I don't need to know the entire process, just really what to input and what to output. And then finally, when I want to send the final scores, I can write the data in a text file that can be opened by another application. So just to wrap everything up, I want to say that so Unity provides us with a lot of opportunities for incorporating things from the environment. There's a number of new devices, especially with the rise in popularity for VR. So there's a number of devices that are being introduced that allow us to connect sensors to VR headsets. And this is one of the easiest ways to incorporate tracking and sensing into the VR experience. Now, if you want to do something that there isn't a solution for, there might be somewhere in the open source world, and it never hurts to go online and see if there's an open source API available for, say, a light bulb that you want to attach to your VR experience. And finally, if none of those work, you may have to be more creative. Maybe you might have to read and write, start by reading and writing text files, but it's possible. So I hope you guys learned a lot from this. Thank you.